So my name is Camilo Lopez, and I work at Shopify, and this is how Shopify sharded Rails on 2013. So a little bit about Shopify. We're an e-commerce platform. We don't sell stuff. We allow people to create their own stores to sell their own products. Let's talk a little bit about the scale of Shopify. Shopify is deployed in around 100 app servers. Hardware is heterogeneous, but in general, it's very high performant. We have around 100,000 active shops now, of which around 88,000 actually pay us money, so 88,000 customers. The stack we're running on now is Ruby 2.1, Rails 3.2, MySQL 5.5 with Percona patches. Some MySQL is kind of important for what I'm going to say. Like some of the things in this talk are MySQL specific-ish. This is a super oversimplified version of what Shopify looks like. We just have a typical Rails stack with the app servers being Unicorn and job servers Rescue, and we have our master database and some charts. This is a typical day for Shopify. We do around 150,000 requests per minute with peaks up to 400K. And overall charts, we're doing around 20K queries per second. Since we are in the business of commerce, let's talk about money a little bit. So the GMV, this is the sales over the whole platform last year, was 1.6 billion. That means like at every minute through the platform, we are looking at someone like almost 4K per minute. So when there's outages, this is how it feels like. So why you should never, ever shard? Sharding is just slicing all your data over more than one database. That's kind of like the definition I'm going for. So Rails and most libraries really like to have one database, and they are very comfortable with that. And it's like a built-in assumption, so you're going to be fighting the system all the time. It makes it really hard to do things you maybe do all the time now. Like if you want to know, you want to group by something on your customers, well, you can't do that anymore. Well, you can do it, but you have to think about it, and you have to prepare for that. Primary keys, it doesn't work anymore. You need to also come up with a scheme for that. Chances are you will have to write your own. There are gems that might help you. There are tips and tricks and stuff, but there's no one-through way of actually sharding any Rails app, so you'll have some maintenance to do forever. Chances are you actually can just buy a better machine, a better master database, or whatever is your problem now. Most of the time, that will get you out of the problem. You can, like for 7 years, we just went tuning MySQL, adding more caching, and going our merry way. That way, it was fine. Like John talked last year, was all about this. So why did we actually shard? It happens that for the last 4 years or something, traffic and customers double each year. It just is the fact today. So we also have Black Friday and Cyber Monday. Since we are an e-commerce platform, Black Friday and Cyber Monday are really, really hard for us. We have like twice the normal load. It is all rights. We can't cache anything because when people are buying, we have to be truly transactional. We have to actually make sure things get written, and there is no cache in any of that. So threading. Shopify is not threaded, but MySQL is. And it turns out like this variable, InnoDB thread concurrency, is what tells MySQL how many threads can actually be operating on your data at any single moment. The normal setting for this variable is around the number of cores you have in the database. So that brings us here. Like, in reality, if your MySQL is properly tuned and your queries are reasonable, the problem is not that setting. The problem is CPU. Your CPU is just not big enough. So this was 2011. We have this configuration to Intel chips. Now in 2012 we had 4. Do we have to buy better CPUs? When you get to 8 CPUs in one box, it becomes really expensive. And well, at this point, we're probably better off using horizontal scaling, being that next year is probably going to be double of this year. And also, oh my God, Cyber Monday is coming. So this is a little bit emotional, but that was it. Okay, well, let's decide that we're going to shard. What do we get from that? So besides horizontal scaling, there's some side benefits. Your more localized buffer pools are going to keep data warm longer, and they're going to trash a lot less. So that's good for overall performance. You also will have smaller indexes, so lookups are going to be faster. Doesn't hurt a win. And failure isolation. If a shard burns down, well, we have half Shopify, which is better than no Shopify. How did it actually happen? So it took the entire year. And before we started, we set out to think what could go wrong and build some constraints. So for instance, we decided that we would have in a Ruby representation of transaction, we would never mix writes to two different charts. That is really important because you can really guarantee that things are going to be transactional across two databases. You could try to use XA or something like that, but the fact of the matter is that it is really hard to get right, and we can probably get around that by restructuring our code. No joins between charts. That is just a fact of life. You can join across databases. You can fake them, but it's probably best to not paper over that inherent complexity. No nested chart selection. This one is a little hard to understand now. When I go over more detail on how things work, you will see it. What happens is we use blocks to declare the chart context, and we didn't want to give developers too much rope to think about switching between charts in one controller action, for instance, or something like that. So you select the chart, you have to get off the chart before changing to a new chart. This had to happen live. It was a team of between 4 and 6 people actually sharding. Shopify now has more than around 100 developers, so everybody else was just adding features and doing whatever they were doing. There was no stop and chart moment. So how did we actually slice our data? This is a typical Redis application in a way. That's what Shopify kind of looked like before. And this is a very simplified schema. So you always have a shop with an ID, and it has a bunch of associations, say product and blog and an order. So you see the associations at the bottom didn't have a shop ID. So the first thing we did, we realized, is that everything is actually scoped to a shop. That was actually an easy realization, but that made things clear from the beginning. Second, we just made sure that we normalize the shop ID everywhere. Even if you were 5 associations removed from shop, you get a shop ID. That's really, really handy when you actually need to move things across shards. Then we added chart ID to a shop. Even if we just have one database, just go ahead and do it. And then we had a goal. This is what we wanted to get to. We wanted to have the purple box that says shard be in a separate database than the master thing that says shop. And it also includes things like domains and things that don't quite route to a single shop. So this was our goal. We would have a master database, this guy. We would have routing data, like domains and shops table. And we would have sharp 0 to whatever number. This would be logically identical. Hardware is different from, they don't have to be identical in hardware, but it always have to have the same structure. What about primary keys? So auto-increment doesn't work anymore. Your IDs will probably stop being unique because they will just increment differently in different databases. So what to do about it? Well, some of you might have heard about Snowflake from Twitter. This is just a service that's going to generate IDs from you from outside the database. So there is a Go implementation called NoEQD. We used it for a while. It works well. We run in production on a table that we could probably break if we had to. However, we needed one more service. That's kind of a bad thing. You don't want to have one more thing that will take your application down. Also, JavaScript does not like big numbers. Our customers can run scripts on their own stores, and some of them are like jQuery that do whatever they want to do, but they rely on the IDs being like processed by JavaScript. So, yeah. We actually could make it work with MySQL config. MySQL config uses MySQL InnoDB actually uses two variables to control what is the next ID that's going to be assigned to the next row on a table. So there is auto increment, that is the interval between successive IDs, and there's auto increment offset, which is where the actual count starts. Then it applies this formula, which is just auto increment plus an n times the increment. So the offset plus an n times the increment, where n is just a sequence, it's just the natural numbers going from 1 to infinity, I suppose. So if you fix on an increment and have different offsets per shard, you get something like this. So if you have like 4 for the increment and offsets of 1, 2, 3, your IDs would actually interleave. So you just create a large offset, like about the number of shards you want to have. And it makes it slightly less flexible when you need to add shards. You have to be more careful with that, but it frees you from having to have another external dependency. So this is the route we went. What about connection switching? So connection switching is important because it's pretty much like what sharding really is. We went for a block-based context API. So we have a sharding module and have like 2 or 3 helpers. They look this way. So you just call with shard, and whatever happens there happens within the context of that shard. So in that block, any sharded model will talk to the current shard connection. A sharded module has to include a module called sharding concern and have a shop ID column. So this is all you need to declare a model being sharded in Shopify. Non-sharded models, they don't care at all. They always talk to the master database, and that's it. How do we route people to different shards? So an HTTP request comes in. We just this is our schema, so it has to come from the internet. It goes from a domain to a shop. The shop has a shard ID, and the request is run in the context of that shard ID. It looks something like this. The shop manager there is like turning that host into a shop. Then we just select the shard, and this is actually running a round filter in the top controller. What about background jobs? Well, if you have a shop ID parameter, then it's actually super easy. You just go and include this module that is going to do exactly what I showed, but put a filter around perform in the background job. If you don't have a shop ID, then I'm going to talk about querying across shards in a little bit. This is mostly transparent to day-to-day tasks. Most developers just go their own way, adding features, fixing bugs, because of the property of most of anything that happened in Shopify being scoped to a shop. So remember those constraints? The existing code didn't know anything about them. And some things like joins across shards were not obvious because we only had one database, so we had to prepare to get to that point, to the point where we could have a second database or a third database and deploy our code. So we wrote verifiers that would log the problem, something like this. You see, there's a missing chart context for this selection. And then fix one at a time. When they were all gone from the logs, then we'll make them race. And at that point, developers could introduce more of these problems. This proved to be really, really useful, but it was a lot of hard work. It took months because people were adding features as we were going, so it makes it a little challenging. What about rebalancing? So do we want to move things across shards? Well, the answer is yes. We took the safety-first approach. We lock a shop entirely and then get it moved. We have two levels of locking. We have exclusive lock that is taken by maintenance tasks or some cron jobs. Why? Because we have less control over what these kind of things do. They can just go and like update everything on a chart at the same time, and you don't want to touch data that is in flight. And we have a per chop shared lock. So this one is taken by things that are iterating over a chop. So it only locks a chop at a time. And when you bump into a chop that is locked, the user has to decide what to do. They can either erase or ignore the data from that chop. The locks were implemented with Zookeeper. We had some configuration problems with Zookeeper. We actually fell back to Redis, but we're going back to Zookeeper because it's just the better locking strategy. There is optimization for the common case. So for HTTP requests, we don't want to be reaching to Zookeeper or Redis for every single HTTP request. What we do in that case is we set this isLocked field in the chops table. And from there, the top-level controller will 503 on the user. The mover is simply a Ruby script, something like that. And this is how it works. So it takes the global lock or just bails if the chop is locked and sets the isLocked to true. Then it waits 100 seconds. At that point, we know our unicorn web servers will be dead because they are configured to kill any request that lasts more than 90 seconds. Then, at this point, the jobs have been released. We can safely fork as many processes we need to copy a table in each process. Then we copy row by row and verify that they actually made it fine to their end. Then we change the chart ID at this point and unlock it, and we're done. What about the old data? Well, seeing all those delete statements going by your screen is kind of not pleasant. So for now, we decided to not automate it. We actually go and run a script we need to clean up shops that are data that is not longer in the proper shard. Why did we not do an online mover? Well, it was just hard. There are some ideas. You can always use a TCP proxy, maybe write to two databases at the same time. Something like that. It seemed to be too much work for what we need now. We'll probably move towards something like that, either using the TCP proxy or replication. So what about joins? You can just iterate and saying instead of joining, you can't just iterate, send in a SQL query, because you might bump into a shop that's been locked, or you can have rows that hadn't been deleted from a move. So what we do is we provide an API that will take the logs as it iterates, and will let the user either ignore or raise. They also have the nice property that will ignore anything that shouldn't be on that chart. We have two actual methods for this. One is query on each shard, which is just going to execute an active record relation on each shard, taking the logs and ignoring data that is not there. So use something like this. You call query on each shard, you pass it a relation, you decide what to unlock, and you do whatever you need to do. There is finding batches on each shard. This one is analogous to find each. It will run things that are like too big for a regular relation. So, for instance, if someone needs to look at a full model on every shard, they're gonna do that. It looks pretty much the same. You just pass a relation, but this thing, instead of like loading the memory, is gonna try to batch it in like small pieces and send it back to you. If someone absolutely needs to run custom SQL, what do we do? Well, then they have to take the global lock, but I'd rather they don't do it. How long did it take us to actually shard? Well, it was entire 2013. So we're here in Cybermonday 2012, and then we started. We actually looked for vendors for like a good month, and I was none actually cut it. On May, we decided that we could use DB Charmer. We stopped using like 2 weeks ago or something. It's actually a very futureful gem, but it has too much stuff. We use like a very, very small subset of what it offers. We came up with the constraints and verifiers, and then we worked for like till May until almost October, only making the code ready for the actual sharding. Then somewhere in October, we came up with the API to query across DBs and the mover and the actual moving of shops preparation for Cyber Monday happened in October and November. So this is what we came up with. This is what you need to do when you want to shard your application. You need to know how you're going to slice your data. You need to do something about primary key generation. You need to come up with connection switching at some point. And the two at the bottom, you want to figure out if you want to rebalance at all. Maybe you can just start a new chart and go from there. And how to query across charts if you even want that. OMG, Cyber Monday. So how did we do? We had about 100K RPM higher than day to day, so it looked something like this. It was interesting. And about 10 to 15K QPS higher. So this is two charts working. Chart 0 is what most people are. Chart 2 is our high availability chart. You can see that it spikes almost to 30K. All these tiny spikes, which are actually huge, are flash sales. Those are particularly interesting because there's some high volume shop just brings 40,000 checkouts in a minute or two. Those used to be really toxic for the platform. Now we can separate like normal people from these monsters, and it works great. Yeah, so this is our archival chart. It's doing like 60 queries per second, not really stellar, but this is what people that are no longer with Shopify are. So when you close a Shopify store, it actually never dies. You can come back tomorrow. But we didn't want all that data cluttering our indexes and just being sitting there making us slow. So we put it here. Even though it's like not doing much, it's actually a win. So we have like 80 milliseconds average response time, not on time, and all-time record sales for that day. The purple line is average. The blue line is P95. So I think it went well. Thank you.